Night. A massive warehouse is already completely engulfed in flames. Dozens of meters of fire rise above the roof, while fire engines arrive at the scene one after another. It may seem that everything now depends on how much water they can pour onto the flames, but very few people realize that the water tank inside most fire trucks contains enough water for only a few minutes of operation. After that, a multi-ton vehicle worth hundreds of thousands of dollars can become little more than an empty tank. That is why firefighters start thinking about something else from the very first seconds. They search for a water source. It could be a fire hydrant, a nearby river, or even another fire engine. A single mistake can cost an entire building. And surprisingly, the most important part of a fire truck is not its water tank at all. The real heart of the machine is hidden deep inside its body. Today, we are going to discover how a fire truck actually works and which engineering solutions help save thousands of lives every day.
Many people believe one simple myth. When a huge red truck races down the street with its siren screaming, it looks like nothing more than a giant water tank mounted on wheels. Some people even assume that the water inside should easily be enough to put out an entire house. But during a real fire, that idea falls apart within the first few minutes. Flames consume everything in their path, and an enormous amount of water is required. A typical fire truck tank holds roughly 4,000 liters. Once firefighters activate a powerful water cannon, that entire supply can disappear in only 3 or 4 minutes. Imagine a huge truck sitting in the middle of a terrifying fire and suddenly having absolutely no water left. That is why a fire engine is not really a tank designed to transport water. It is a sophisticated mobile pumping station that must continuously draw water from outside sources. And this is where a fascinating engineering problem appears.
What happens when there are no city hydrants nearby, and the only available source is an old rural pond or a deep well some distance from the road? Firefighters throw their thick hoses into the water and switch on the pump, but nothing happens. The reason is that the main pump inside the truck is designed to move a heavy liquid. Its spinning blades cannot simply grab lightweight air and push it forward. If the pump is empty, it will keep spinning uselessly, desperately trying to move an invisible gas. The truck itself cannot take even a single sip from the pond. To solve this problem, engineers came up with a clever trick. Hidden inside the vehicle is another small but highly specialized pump. Before the main pump begins operating, this device starts pulling the air out of the pipes and the submerged suction hoses. A near vacuum is created inside the system, and then an amazing law of nature takes over. The surrounding atmospheric pressure pushes down on the surface of the pond and forces the water upward through the hose toward the empty pump system. The water can rise several meters against gravity, driven by the pressure of the atmosphere. As soon as sensors detect that the hoses have filled with water, the smaller priming device shuts down, and the powerful steel heart of the truck takes over. Now the vehicle is ready to move tons of cold water toward the fire. But doing that requires almost all of the strength produced by its engine. Once the water has completely filled the empty pipes, the truck's most important machine comes alive. There is a common belief that a fire engine contains a giant mechanical piston, similar to an enormous bicycle pump, simply forcing the liquid outward. But that is another misconception. If engineers used such an old-fashioned design, the water stream would barely reach the second floor, and the mechanism would quickly break under the enormous load. Instead, hidden toward the rear of the vehicle, behind the back compartment, is the true heart of the system, a powerful centrifugal pump made from extremely durable metal. Inside its circular housing, a specially shaped wheel fitted with curved blades spins at tremendous speed. When water enters the center of this rotating impeller, the blades grab it and fling it outward toward the edge of the housing.
This is where centrifugal force does its work. The water is driven outward and converted into a high-pressure flow before being forced through the narrow outlet pipe. That enormous energy allows the water stream to travel upward and reach windows on the higher floors of modern buildings.
But another serious engineering challenge now appears, one that pushes the entire system close to its limits. A normal vehicle engine is designed to cool itself most effectively while the vehicle is moving quickly, because air rushing through the front grille continuously cools the radiator beneath the hood. During a fire, however, the multi-ton truck may remain stationary for hours in the middle of intense heat and suffocating smoke.
At the same time, its huge diesel engine is not merely idling. It is operating under an extreme load, using its full power to keep the steel water pump spinning. Under these conditions, an ordinary truck engine could overheat and seize after only a short period of operation. To prevent that, engineers had to redesign the way the engine's energy is distributed. Between the normal transmission and the vehicle's wheels, they installed a crucial intermediate mechanism known as a power takeoff. This remarkable component can redirect hundreds of horsepower wherever it is needed. When the driver activates the special control inside the cab, heavy gears inside the system engage, disconnecting the wheels from the engine's power output. Now the engine's enormous force is no longer being used to move the truck forward. Instead, that energy travels through a long steel shaft directly to the water pump.
The engine begins roaring at high power, forcing the steel heart of the truck to rotate at thousands of revolutions per minute. The vehicle remains firmly planted on the ground, effectively becoming a gigantic energy station, capable of moving what seems like an entire river in the fight to save human lives. But all that power needs a safe path for the water. As the engine's energy reaches the pump, a powerful stream begins rushing outward. There is another popular misconception that all fire hoses are basically the same and are made from thick rubber. In reality, they fall into two very different categories, and choosing the wrong type can bring an entire firefighting operation to a halt.
The long, flexible hoses that firefighters carry into burning buildings are designed specifically to discharge water under high pressure. Their structure contains strong synthetic fibers covered by a smooth inner lining that allows water to travel through with minimal resistance. When these hoses are lying empty on the ground, they are flat, like strips of fabric. They only expand into their familiar round shape once pressurized water enters them. But if someone tried to connect one of these soft hoses to a pond and use it to suck water into the truck, disaster could follow. The pump would begin creating suction. The pressure inside the hose would fall, and atmospheric pressure would crush the flexible material inward, completely blocking the passage.
That is why firefighters use completely different hoses for drawing water from ponds, rivers, and other water sources. These are large, heavy suction hoses, designed to remain rigid and circular even under powerful vacuum pressure. Their secret lies deep inside the thick rubber wall. Engineers permanently embed a spiral of heavy steel wire inside the material. This metal spring acts like an internal skeleton, preventing the enormous suction force from collapsing the hose. It keeps an open passage for water, even when the source is a deep well. But bringing the water into the truck is only half the battle. The firefighters must also deliver that water onto the flames while remaining at a safe distance. During the largest and most dangerous fires, ordinary handheld nozzles are not enough. That is when the truck's main weapon comes into action. It is the deck gun, a massive steel water cannon mounted directly on top of the vehicle. From a distance, the device can look no more complicated than a large garden sprayer. But behind that simple appearance is some serious physics. The cannon can discharge dozens of liters of water every second, generating enormous recoil. The backward force is so powerful that a mistake in the engineering calculations could cause the cannon to damage its own mounting or even destabilize the multi-ton truck. To control this force, engineers carefully shaped the internal passages of the cannon, using the movement of the water to reduce some of the reaction forces inside the metal body. The entire cannon is firmly attached to a powerful steel frame connected to the vehicle, transferring the recoil through the chassis and into the wheels and the ground. The firefighter can also remotely change the shape of the water stream. With a simple adjustment, the dense stream can become a concentrated water jet capable of striking a powerful target, or it can spread into a wide cloud of tiny droplets. That fine spray absorbs heat extremely quickly and can create a protective curtain of water around firefighters and equipment, preventing intense temperatures from reaching them directly.
The firefighter can also remotely change the shape of the water stream. With a simple adjustment, the dense stream can become a concentrated water jet capable of striking a powerful target, or it can spread into a wide cloud of tiny droplets. That fine spray absorbs heat extremely quickly and can create a protective curtain of water around firefighters and equipment, preventing intense temperatures from reaching them directly.
If a huge amount of water is poured onto burning gasoline, the fuel can remain on top of the water, continue burning, and spread outward over a much larger area. Instead of stopping the fire, the water may help the burning liquid move. To deal with these dangerous fires, engineers installed another specialized tank inside the truck. It contains a concentrated chemical agent known as foam concentrate. The mixture is produced through a clever device called a foam proportioner. As water from the main pump races through the pipes, the proportioning system uses a precise valve to draw a controlled amount of chemical concentrate into the moving stream. The quantity is usually only a small percentage of the total mixture. At the end of the hose, this mixture combines with ordinary air and rapidly expands into a thick, sticky, lightweight foam that resembles a blanket of soap. The white foam spreads across the burning fuel and cuts off its access to oxygen, without which combustion cannot continue.
The flames quickly begin to die beneath this protective layer, while the foam remains in place for much longer, helping prevent surviving fuel from catching fire again. But how can firefighters control all these violent streams of water when several teams are working simultaneously on different sides of a burning building?
Many people imagine that a fire engine simply has one hose connected to it. That is yet another myth. Hidden inside the rear compartment is an actual water distribution system known as a manifold, filled with valves and control points. From this single distribution center, water can be directed simultaneously toward the roof-mounted deck gun, into the foam system, and through several handheld hoses being carried by firefighters to different floors of the building. Engineers also had to solve another difficult problem: how to keep the pressure stable for everyone using the system. Inside the manifold are specialized relief and control valves that respond to sudden pressure changes. Imagine that one firefighter inside a burning building suddenly closes his nozzle while moving into another room. At that exact moment, a huge volume of rapidly moving water encounters the closed valve. A dangerous pressure surge can appear. This phenomenon, known as water hammer, can damage pipes, fittings, or hoses, and can even make a hose extremely difficult to control. The truck's pressure control system detects the sudden rise almost immediately and releases the excess pressure by redirecting water through the system or back toward the tank. As a result, the other firefighters can continue working without experiencing a violent pressure shock. But even when this balance appears perfect, another invisible threat can develop inside the rapidly moving water itself. At the height of firefighting, when everything seems to be operating normally, an invisible enemy can begin forming inside the pump. There is a common misconception that ordinary cold water cannot damage extremely strong metal components. Some people imagine that a stainless steel part could only be destroyed by a large physical object, such as a stone or piece of wood accidentally entering the system from a dirty pond. But that assumption is dangerously wrong. Water can damage even strong metal through a phenomenon known as cavitation. When pressure inside the pump falls below a critical level, something extraordinary begins to happen. The water can start forming vapor bubbles, even though its surrounding temperature seems completely normal. Millions of microscopic vapor bubbles appear within the moving liquid. They travel with the water until they reach an area where the pressure rises again. That is when the real damage begins. The vapor bubbles do not simply disappear gently.
they collapse violently inward, creating tiny but extremely powerful shockwaves. Billions of these microscopic impacts can strike the spinning pump blades again and again. The force can gradually remove tiny pieces of metal from the surface, leaving behind pits and deep cavities. Eventually, the component can look as though its surface has been eaten away. The pump may also begin producing an unusual, disturbing rattling or crackling sound, almost like stones being shaken inside the machine. If the phenomenon is not corrected, the expensive pump can suffer serious damage at exactly the moment firefighters need it most. To prevent this hidden threat, engineers equip modern fire trucks with pressure monitoring instruments and control systems. Drivers are trained to watch the gauges carefully and avoid operating the pump outside its safe range. At the same time, another critical problem is developing under the hood.
As we already know, the massive diesel engine may operate at high power for hours while the truck remains completely stationary. The conventional cooling arrangement found on ordinary heavy trucks can struggle badly under these emergency conditions. When intense heat surrounds the vehicle and burning materials fill the air with ash and smoke, the radiator can become contaminated with debris. The hot air around the stationary truck also provides much less cooling than the airflow created during normal driving. To protect the engine from overheating, engineers developed additional heat management systems that can transfer excess engine heat into the firefighting water circuit. Part of the cold water moving through the truck can pass through a heat exchanger, absorbing unwanted heat from the engine's cooling system. This creates an elegant engineering arrangement.
The same cold water being drawn from a hydrant, pond, or other source to fight the fire can also help carry away heat from the hard-working diesel engine before continuing toward the hoses. The engine remains within a safer operating temperature range, allowing the truck to continue pumping for long periods without suffering catastrophic overheating. But controlling this enormous combination of fire, machinery, pressure, and moving water requires something else: a technological brain. As the firefighting operation approaches its most critical moments, some of the least visible components become among the most important. Managing all this hydraulic power is no longer a matter of an operator manually adjusting every valve and trying to balance pressures by eye. Modern fire trucks use sophisticated electronic monitoring and control systems to help maintain stable operation. Imagine that firefighters inside a burning building accidentally bend or compress a heavy hose. Without proper pressure control, the pump could continue forcing water into the restricted line, causing pressure to rise rapidly and potentially damaging the equipment. Electronic monitoring can detect sudden changes in pressure and flow extremely quickly. Depending on the system, automatic controls can adjust pump speed or redirect water to keep the system within safe operating limits. This invisible layer of electronic protection reduces the chance that a sudden human mistake or equipment problem will turn into a major failure during the most dangerous part of an emergency. But the engineering of a fire truck is impressive for another reason as well. Have you ever wondered how these enormous vehicles, loaded with thousands of liters of water and heavy equipment, can race through narrow city streets and still remain stable during sharp turns? There is a common myth that a fire truck is basically an unstable tank on wheels that could easily tip over whenever the driver makes a sudden steering movement. The reality is very different. Engineers spend enormous effort controlling the vehicle's center of gravity and distributing every kilogram as carefully as possible. The heaviest components, including the large water tank, pump, and other major equipment, are positioned as low as practical within the vehicle's frame. The side compartments are also arranged according to strict weight distribution principles. Heavy rescue tools, hydraulic cutters, power equipment, and other dense objects are stored in lower compartments, while lighter equipment, such as protective clothing, masks, and medical supplies, can be placed higher. This careful weight distribution gives the multi-ton truck a much more stable stance on the road. It allows the driver to maneuver through dense traffic and tight streets with greater confidence while rushing toward the emergency. And when the final flames are finally extinguished and the smoke begins to disappear above the warehouse,
the fire truck's work is still not finished. A strict and essential maintenance routine begins.
Firefighters cannot simply park the vehicle and leave it covered in dirt. Residue from chemical foam can dry inside the pipes and valves, potentially damaging expensive equipment. The internal passages of the pump and water system are carefully flushed with clean water. Wet fabric hoses are taken to specialized drying areas or towers where they can completely dry out, preventing moisture from damaging the material. Fresh, dry hoses are then placed back into the equipment compartments, carefully folded or rolled into compact coils. The empty water tank is refilled, ready for the next emergency. The foam tank is replenished with the required chemical concentrate, and the truck's fuel tank is topped up as well. After all of these checks, the giant red machine once again sits quietly inside the station. It may look completely inactive, but beneath that silence is an extraordinary combination of pumps, valves, engines, electronics, hoses, pressure control systems, and carefully engineered structures. And the moment another emergency siren sounds, this enormous machine will spring back into action, racing toward another fire, and relying on all of that hidden engineering to help protect people, property, and human lives.